Thanks, Tusi, and hello everyone. Let's look into the BigMAC firmware implementation. So the BigMAC firmware is constructed based on Python 3.5 and SWA Prolog APIs. So it employs the Network X library for the graph construction and the SE tool package for decoupling the SE policies from the Android images. So the implementation comprises the four blocks: the firmware extraction, the system boot emulations, and Android credential simulations, and logic-based query engine. So here, author uses the open source extraction library for the raw form. It supports 18 form vendor and they extended to support Samsung image as well. So, but the author primarily focusing on extracting the Google, Samsung, and LG images. Yep. So, as part of the extraction tool, first the recursively unzipping each layer of the images based on the file type and using the ext4 disk image extraction routine to maintain DAC and MAC information as well. So in the second, this tool does a walkthrough on each image and fetches all the metadata provided by the three API calls called state, getX, attributes, and readline. So these all extracted metadata will be stored in the dictionary file for the further process. And then using the virtual system, the author will extract every file including build.pop file. So all the files in this image as well as the build.pop, which encompasses metadata such as Android versions and hardware configurations. So finally, all these extracted raw files will be stored in their image specific database for further processing. So after static firmware file extraction, the author emulates the Android system boot. But the issue is the author doesn't know the process running on the firmware. Yeah, so the author says that to understand how the system policy would apply to these processes, we should know what are all the processes running on the real phone during boot, including their permissions and the runtime credentials. Without knowing this, the cross-vendor analysis would fail on the scaling. So here the Android booting process is well defined by the platform. That's it. Yeah. So Android kernel starts similar way as the desktop Linux kernel starts. So inits here its very first process. We can say it is a root process or grandmother of all the processes. So init process has two responsibilities. One is to mount the directories and then running the init.rc scripts. So author mimicked the init.rc and they implemented the commands such as mkdir, ch1 and chmod. Change the state of the file system including the DS information, and followed by trigger it rises an event, and the enable command it starts all the booting services, and followed by the mount command it's mount all the file system to the hard point. Yeah, so there is a little challenge in booting emulations. So here the each vendor and device model comes with its own set of behaviors in the init system. So for instance, the Pixel 8.1.0 image during the system boot, it creates a slash data directories. For author to do this, for author had to set the property called the whole decrypt to trigger the post decryption in the init actions. And the second one, the author discovers another behavior associated with OEM called the original equipment manufacturer. They add their custom groups and user IDs that deviates from the Android platform, so which is unable to map these names to the existing IDs in the extraction Android files. So to fix that, they are extracting the Android IDs from the Android libc.so binary file in order to just overcome these all challenges while emulating this booting system. In the credential emulation, after booting init and modifying the file system, the author recovered the service definitions from the init files to properly assign the runtime credentials to inflated processes. So these service definitions contain, in the Android users group and capabilities information. And followed by here as part of the logic based query engine, the author used the SWA Prolog 5 constructed this logic based query engine and provide all four query interfaces to pass the output from the Prolog, which means the list of paths. Yeah, then the author created interact query front end using the GNU readline library. This gives us support for the interactive tab completion of all the possible processes and objects to use source and target nodes, and also allow us to save, restore, and print all the queries. So within Prolog, the author needed to add cutoff parameters to prevent length values is beyond the values specified, which means the path values. And the author also implemented is unique, which is used to filter the paths that contain duplicate elements. And then to collect all possible paths, the author uses the Prolog's depth first search DFS with interactive deepening. Yeah. In total, the author wrote of 5,997 lines of Python across the extraction tool, graph, creators, and query front end. And as part of the Prolong engine, they were written, 343 lines. So that's it. So let's Maldi continue the remaining part of the paper.